Well, hello everyone. Welcome back to Zomboland Gaming. I am Zombo Skater, and it has been 6 months since we last did a Turing Complete episode. I apologize very much for that, but this is one of those games that you really have to be in the right mental space to want to play it, because it's not like you're just playing a game. You really have to dive deep in order to solve these puzzles, which is kind of what this game is really about, is a puzzle of learning how to build a computer, but at the same time, it's a great way to actually learn how to build the inner workings of a computer, right? Which we've seen in the last 6 episodes. So I had to take a break from it. But anyway, we are now back, and after 6 months, there's been a lot of changes that have been made to the game. So we're going to have a long episode because we are going to cover all of the changes that have been made to my levels, as well as talk about a few of the functionalities that have occurred in the last patches. And then we are going to cover 2 levels that were added since we last did this episode, and 3 levels which will get us to a Turing Complete state. We will be done with the CPU architecture portion of the game. So without further ado, I'm going to cancel my webcam, and we're going to get right on into it. And I'm going to try not to just go blah, 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 and try and be concise as I can about these new solutions. And hopefully it all makes sense, but I'm going to timestamp everything down below so you can skip around to whatever level you need to go to. And yeah, you have any comments, questions, concerns, different versions of solutions that you want to share, or anything like that, definitely comment down below, and we'll talk about them in the next episode, which hopefully will come a lot sooner than 6 months. But anyway, without further ado, webcam gone, let's get on into it. All right, without further ado, so right off the bat with the main screen here, you can hear under options, we have music. So that's kind of cool. So they added a soundtrack to it. It's actually not a bad soundtrack. It kind of keeps you motivated as you're playing around. But we also have this right here, allow circular recipes, which doesn't quite seem to be working for the campaign. So I'm not exactly sure what's going on there. But hopefully that's going to be something that means that your solutions in-game will work more like a real-world scenario where you have multiple inputs and outputs connected to similar lines. But we'll get into that later. So we also have sandbox mode. So this over here means you can just kind of come in and put down various little bits and bobs and connect inputs and outputs and do all sorts of things here. So we'll be able to test out various features outside of the campaign and make our own circuits up. So that's kind of cool. But really what we wanted to get into was the campaign. So if we scroll on out, we can see, boom, we are done all the way up through working a computer now, which these 3 levels right here, what we're going to focus on at the very end of this this episode. But that's all we have left. We appear to be more than halfway complete. However, the work that's going to have to go into completing these levels is probably going to be tenfold over what we've already done. So let's bounce on into it. So the main things that have changed for me is that circular dependency became a really big issue. They revised some things that caused a lot of prior solutions to now no longer work due to circular dependency, as well as they removed inputs and outputs, like the ones that the game actually gives to you, like the little byte and bit inputs and outputs that their inner working program does your solution, right? They got rid of some of those, forcing you to have to redo the levels. So right off the bat, these first 3 were fine. The AND gate was fine, but my NOR gate solution no longer worked. I don't need to look at that. I need to look at schematics. So this was our original NOR gate solution, which originally worked. You had input 1 and 2 both going to a NOT gate, so whether or not one of these was turned on, it would be inverted and turn the signal off, and that sufficed. However, what we had to do now, because that input's being connected to the NOT gate caused circular dependency, what we've done here is now looked at if I have one, let's go internet. So if we look here, this is just the first thing that popped up on Google for me. If you look down here at the NOR gate circuit, this is basically what we're doing. We're taking universal gates, which would be a NAND gate, and creating other gates from those. So this NOR gate here is just built off of 2 NAND gates where you've just took the input and put it to both pins of one NAND gate, and then those 2 outputs of a NAND gate go to the next NAND gate, which is acting as an actual NAND gate, and then the fourth and last NAND gate is acting as another NOT gate. So you could actually think of this as two NOTs into a NAND and then NAND it out. So we'll go ahead and cancel out of that. All right, so back in here. So you've got, like I said, you've got your input from A going to both pins of this first NAND gate, and essentially what that's doing is if you're off, you're on. And now if we turn input A on, you can see that the output turns off, right? Same thing goes for the B. If you have it going to both pins, and it's basically just going to essentially swap. So on turns off turns on, right? And so we can see here, if we step through our program, our first inputs to the NAND gate are off, so we swap them, invert them basically to on. The only way a NAND gate ever turns off is going to be if both of the inputs are turned on, right? So boom, if we have one input on, both inputs on, that's gonna actually output. So with them both being turned off, we've inverted these inputs to on. The output of this NAND gate is off, which then gets inverted through this NAND gate back to on again. That is a very lengthy explanation, maybe better served by this alternate version that I put together, which is just using the 3 NOT gates in a NAND. Same thing, but step it on through. You can see as soon as we turn A input on, it inverts this off, which means now this NAND gate is not suffice to turn it off, so it turns on, inverts to an output. Then we just swap it over to the B input instead of A, and then both inputs are turned on, which means now you've got no signal to this NAND gate, which inverts the output, and then inverts again to an off state. So that was the revised workaround solution for that. The OR gate is essentially the same thing. We had a circular dependency on it. We basically just had it going straight to the output before. So all we've done here is built off of that universal gate circuit, and because now we don't have to NOT the OR gate, we just remove that final NAND gate to get our solution. So that was the only change there. Let's move on to exclusive OR. Exclusive OR, this was our original solution, which this is based off of like what you learn in the basics of school, engineering school, whatnot, right? For an exclusive OR gate. Essentially, you have one input that is inverted to an AND gate, and then the other signal goes to the second AND gate, and then vice versa. The B input, the inverted signal goes to the AND gate that's with the base symbol, the prime symbol of the first input, and vice versa, and then those just get ORed together. So it's, you know, if this is made, or this is made, or both, right? So what we ended up doing here is we made a different circuit. Well, it's not a different circuit. It's the same one, just kind of cleaned up a little bit, right? I could have made this a whole lot better. So what I ended up doing, because they removed my input, you can see it right here. I've got no input to actually run this stupid thing. We just cleaned it on up. So essentially, this NAND gate and this OR gate are acting as the two AND gates with one inverted input to them. So if we step this through, you can see right now our inputs are both off. So let's go tick 0. Both inputs are off, which means this NAND gate is turned on, because no matter which one of these inputs is on, the only way this turns off, once again, is if both inputs are on. So this line is pretty much always going to be on unless both A and B are on, which means this AND gate is going to always feel this signal unless both inputs are on. This OR gate only needs one or both to turn on. So since they're both turned off, this OR gate doesn't turn on, so which means this AND gate is not sufficed, so there's no output. Go to the next tick where A input is turned on. You can see this NAND gate is still turned on because you got one signal off on the other side. The OR gate is now sufficed because one input is going through it, and now both inputs to this AND gate are made. Boom, we've got an output. Swap over to the B side, same thing, it's just vice versa. Now we turn both inputs on, which means this NAND gate is now met the circuitry for the only way a NAND gate is going to turn off, which means this AND gate doesn't feel a presence. Boom, it is now turned off. So that's our exclusive OR gate fix. Much simpler with just the 3 gates. And then essentially, because of doing that with the exclusive NOR, essentially all we did is, this was our default version, right? we got given the exclusive OR gate, so I was just lazy and said exclusive OR with a NOT, and cool, that works. However, I wanted to show how we build off of the actual exclusive NOR that we just did. And so all we have to do is invert the output, right? What better way to do that than just swap our AND gate to a NAND gate? Now we've inverted the output, and it works the same exact way. We'll just step it through. Boom. So there we go. The only way that this output of this exclusive NOR is if both are on or both are off. All right, so that deals with all the basic logic circuitry. Now we're going to move into arithmetic. Arithmetic, we start with, I believe, double trouble here. Default circuit. So this was our default circuit. There was two problems here. One, they removed my inputs. Two, these three AND gates going to either side of this OR here are going to cause circular dependency. So our workaround for that was essentially, one, I cleaned it up. So now you can see 1 meets 2, 1 meets 3, 1 meets 4, 2 meets 3, 2 meets 4, and 3 meets 4 is the inputs to these AND gates. And they give us 3 input OR gates up here. So we've just added in these 2 3 input OR gates to prevent any circular dependency. Otherwise, it's the exact same solution as before, which is nice. Counting signals. Where is that one? Counting signals. So counting signals, we originally had this this version by Zen Dragon, who had mentioned it in the comments below. Very, very nice. We discussed this in a prior episode. However, this exclusive OR and this AND gate are now causing circular dependency on bit 2 of the output here. So all we did for that to fix it was just added an OR gate. Just basically making a buffer in between this output. So no circular dependency can happen, because whether this or this is made, you're going to get an output on it. So there we go. So that was the difference and change there. The switch level has been moved over into memory and called bit switch instead. So I don't know what happened to it or why they decided to move it over there, but there you go. 1-bit decoder. I believe that is up here. Yeah, 1-bit decoder. So our prior default, we used an SR latch, which in a prior episode, they had changed the SR latch, got rid of it, and turned it into a delay line. So basically just once you input, 1 tick later, the output will show what the input was. So they just got rid of the SR latch, so this no longer worked. And then I believe what we did was we made a very overcomplicated decoder, mainly because my thought pattern here was this orange line to the pink line here, that's our actual 1-bit decoder. But in real life, most of the logic chips have an enable circuit. So that's where I was going here. Here's my actual decoder, but I added in an enable line to an AND gate. And then, of course, they removed all my components in the update. And so here we go. So this is our new solution, because we don't have to have the enable line for this game. So to keep things simple, I literally just have one NOT gate, because if the input turns on, like boom, you can see the input turns on, we get an inverted signal to the first output bit and an actual on bit to the second bit here. And then vice versa. If I turn this back off, you can see we swap around. So boom, boom, made. So I just simplified it. I took the enable line off. That's all we did there. Solution otherwise was the exact same. One way, our 3-bit decoder was actually fine. And then one way. So one way, let me see, where was our actual default? Boom, here we go. I originally used a switch, which still works. For some reason, though, I don't... Yeah, it does actually step through it. So you can actually see this still works, because this switch is causing the signal from this side. If this input/output turns on, the signal will never flow through the switch. But once again, I had to add an enable line. So instead, what I did was, I think, oh yeah, this was just us showing an octal bus transceiver, because essentially that's what we're discussing here, is allowing flow from one component to another component on a bus, but keeping the bus from being able to go back and forth willy-nilly to other components. So all we did here was just made a version of a buffer, because we currently don't have a buffer bit available, I don't think. Yeah, we don't have a buffer bit available. So all I'm doing here is I'm using 2 NOT gates, because we want whatever signal is coming from the left, because that was the thing here. It says make sure the signal flows only from left to right. So we want to make sure that whatever the left signal is, is what we're seeing on the output to the input/output on the right. So you have to invert it twice in order to be able to get the same signal. So I'm just using 2 NOT gates here to invert the signal twice. So we feel this here. However, no matter if this this input/output turns on, it'll never flow back to the left. So we can step it through, and you can see this left turns on. You see the green highlighted here, meaning that this input is felt over here. You turn the right side on, and you can see that we still are off here at the output of this NOT gate because we are off over here. So that's all my change was. It's kind of just making like a little bit of a buffer circuit up until the point that we actually get buffer circuits. And I believe Logic Engine used to be under CPU architecture. Like, I think this used to be pushed up here, so I'm not sure why it's now down in Arithmetic. Maybe I'm wrong. Maybe it has always been in Arithmetic. I don't know. But our Logic Engine is still working just fine. However, this was when I noticed that you can see these little dots at the top of the level. So 8-bit NOR, 8-bit NAND, 8-bit AND. That's showing you what gate, what piece of a little component they're going to give you when you complete that level. So after we complete the 1-bit decoder, they're going to give us a 1-bit decoder. When we complete the 3-bit decoder, they're going to give us a 3-bit decoder. So that's kind of cool. Hadn't noticed that before. I think it was a pretty good change. All right, so now on to memory. Let me see. So delayed lines. This is something they added a while ago. Don't think we even have. Yeah, so I think my default, essentially, it wasn't working, so I just had to redo it, and I color coordinated to show input output. And all this is that when this is off, the next tick, the off state will go into the output. When this is on the very next tick, the output will go. So it's going to take 2 ticks for this value here to show up here. So if we step this through, you can see we're off. On the very next tick, this turns on, but because the input turned on, and we've already got our output here. But on the next tick, now this is turned off again. However, because we stored that 1 in here, now it's felt out here, which is felt on here, which means the next tick, this is going to turn on. And boom, there you go. You can see it turned on. So it's just taking 2 ticks of the game to get to this point right here where the signal felt here is felt here. That's all this was. Nothing has changed there, though. Odd ticks right here. So for some reason, I think, because you can't see what the old version of the game was, I think our desired output used to be swapped where it was on, off, on, off, on, off. However, because this was our default circuit right here, where we had the delay going into a NOT gate, and then the output of that NOT gate fed back into the delay again. So the only way that this truth table is going to meet was I had to move the NOT gate to the top here. So now the output of the delay buffer is going straight into the output, but then it comes back around into the NOT gate to feed back in. So we're still getting that knotted input to the backside of the delay there, the delay line. However, the delay line is outputting straight out. So now you can see boom, boom, boom. It just keeps toggling itself back and forth, which is essentially like an SR-NOR latch. I don't know why they got rid of it, but essentially there you go. Only on the odd ticks is this thing turning off. This confused the crap out of me. Why they gave you an input bit when it's not used is beyond me, but there you go. You can just toss that in the junk pile because it won't let you delete it, but there you go. All right, bit switch, I believe, is the next one. Bit inverter, bit switch. So this right here was the new level that they added. They got rid of what used to just be called the switch level. I don't know why, but what they want here is if components output different values on the same wire, you get an error. However, some components have gray output pins. These are not outputting at all when the component is not enabled. Oh, I got the hiccups. This is the case for the bit switch component. So you can see here, you've got a gray on the right and then red on your input, and then the top is your enable bit. This means that more than one of these gray output pins can connect to the same wire and not cause an error as long as only one of them is enabled at the time. Using 2 NOT gates and 2 switches, build an exclusive OR gate. So what was cool is this is the first time I saw up here, there was actually a number next to the switches and the NOTs that said, 2. So as you use them, they only let you, grade itself out once you had all of the available bits to use. all we're doing here is think of this switch as an AND gate. So if we go back over to our, where was that at? Our exclusive OR gates, and let's go to our original default one. Actually, let's go to the new circuit because that's colored. Ooh, wrong thing to move. So you can see here, we've got an AND gate with this knotted input, right? Knotted input AND gate. Think of the switch as this knotted is going to the enable of the switch, and then the actual input value is the non-inverted version going in. And then, of course, because the output of the switch has the gray and only one can be turned on at a time, we don't need this OR gate because no circular dependency is going to happen. So now if we go back up here to the bit switch, you can see inverted input going to the enable of the switch, and then the opposite side's input is going directly as the value of that switch. So as soon as one of these is turned on or off, it's going to allow the output to come out, and then essentially this is the where the OR gate would be. So let's step this through, and we already know how an exclusive OR works, so this should make sense. So with nothing turned on, both of our switches are enabled. However, there's no actual input value going through, so you've got no value coming out. If we now turn on the A input, it is going to disable the B input switch, but it's going to have the value go through this switch, whereas since B is turned off, it enables this switch, allowing the value to come out. Now you have an output. Vice versa, it just swaps over to the B side. And then when we turn both inputs on, that's going to invert the signals, disabling both switches. So now there's no output coming out, and you can actually see it's gray because there's like legitimately switches not turned on whatsoever. It's not a zero signal coming through. It's just not turned on in this case. So there you go. Exclusive OR using switches. Kind of cool. So that was the new level. So let me see, the bus. The bus is the next one we're going to talk about. This is the next new level that they added. So this level has 2 byte inputs, which are these, and 2 byte outputs, which are these on the right. Your goal is to copy from one of the inputs to one of the outputs. The first bit input, so this is the bit inputs right here. These are the enable lines, determines which input you should copy from. So this first portion of the circuit is copy. The second bit input determines which output you should copy to. So this is our write function. So this is read, write, save, load, copy, write, however you want to think of it, right? Check this hint if you get stuck. Use switches to put the inputs on the same wire. So an even bigger hint is something we haven't discussed in this episode, but we did in a prior episode, is input selector. So if we look at this circuit here, it looks a little bit different than what we're seeing on the new level. But once again, you have an enable line going to a NOT of the switch. This is our 1-bit decoder, basically, right? So an enable line going to a switch, an inverted enable line going to the other switch, which means no matter what this input is, only one of these switches will be enabled at a time. Input 1, input 2. So that's all we're doing here is we're using our input selector with a 1-bit encoder to come up here and where's it at? Where's the bus? Hello, the bus. Hello, the bus. The bus right here. So this is our copy line. So we've got a 1-input selector selecting which one of these inputs is going to allow a signal out. And because our switches are gray outputs, means we can combine these outputs to both of the inputs of the next switch, which is why you see this common line just connected here, right? And then our second set is the exact same circuit as before. However, this enable line, 1-bit encoder enable line, is going to select which of the outputs we're going to go to. So let's go ahead and step it through. So it says copy the value from the correct input to the correct output. Tick 1, copy the value from input 1. So they're calling these input 0 on the top, input 1 on the bottom, output 0 on the top right, output 1 on the bottom right. So copy the value from input 1, which is 34, to output 1. So they've done this for us. We don't turn these on or off, right? So they've enabled this copy function, which enables the switch for input 1, but disables the switch for input 0, putting that 34 value on the bus here. And then they want us to go to output 1, which means this enable line is turned on or set high to enable this switch, allowing the output through. Let's step to another one. Once again, input 1 to output 1. So now we're just a value of 212. copy the value for input 0 to output 1. So now we've set low this enable line, which is going to enable the switch for input 0, putting that value on the bus, but disabling input 1. And then we're going to leave the enable set high for switch for output 1, allowing that value to go there. And there we go. So that's all that is, right? So that's just kind of getting you used to the fact that you're going to have a common bus that is taking values from multiple different places to put it multiple different places as as needed. Okay, so I wanted to talk about little box and saving gracefully, or saving bytes. However, if I click on this, it's going to crash my game, so we might as well just do it. Look. Oh, whoa! It actually let me this time! Woohoo! Woohoo! So, okay, earlier this didn't work. Earlier this didn't work. This is excellent. This is excellent. All day today, it's been crashing my game big time. So here we go. Good. So default, all they did was removed all of our components and all of our inputs. So let's go here to saving bytes. All I did was copied and pasted. That's it. That's all we did. I believe also, oh yeah, so they have an enable line now. You can see before I used a switch right here. That's where this input 1 line comes down to, and there was a switch, and I was enabling using a switch the output. However, they actually added an enable line. Like if we click on the output, it doesn't show it. Does it have down here? No, it does not. So this little bottom side is an enable pin for the output. So all we did was, instead of use the switch, just put the enable line straight to the output. That was the only change to saving bytes. Oh god, let's see if we get lucky. Can we click on little box? Yes, we can. Let's go to the default schematic, which is a higgledy-piggledy mess. It works, but it's a higgledy-piggledy mess. I think I was trying to work on a new circuit. All we did here was, once again, I believe, what did we do here? Oh, okay, so all this and not gates is our decoder circuit. I removed the decoder circuit and actually used a decoder, so we can see that right here, as we're just using our 1 to 3 decoder here. I can't zoom in any farther, so that cleaned that up a little bit. And then let me see. I think, oh yeah, we removed the switches and actually replaced them with AND gates. So you've got all of our AND gates here doing the exact same functionality. I just was able to remove all the enable lines because of that. I essentially just have the outputs of these decoders going to the extra input. So I'm using 3 input AND gates here. So you've got bit 1 with the enable line from both this decoder and this decoder, coupled together for a save and A or B or load functionality. That's all we did. We just removed switches and replaced them with 3 input AND gates. Also removed my big decoders and actually used the physical decoder component that they gave us. That's all we did. So I'll pause it right here. That way you guys can screenshot it or pause it or whatever and look at this version. And once again, here was the default. Same thing, works exactly the same. It's just the new version is much cleaner. Much cleaner. So there we go. Whoa, that's cool. That actually worked. All right, now into the final section. Look at this right here. Woo, this has been a long video. So once again, Logic Engine still works just fine, but it is down in architecture now. Arithmetic Engine. Let's go to our default. Let me see. Cleaner. Let's go to the cleaner one, because this would be the one that we actually used. So you notice here, here's our arithmetic section right here, which is, I went basically to 1 adder, and I just had using switches, whether or not we were in the subtract or adding mode to that 1 adder. In the new circuit, we actually have just done 2 adder circuits. One is specifically for subtracting, the other one is specifically for adding. Here was all our functionality for the OR, NAND, NOR, and AND circuitry. And then we once again used a giant handmade decoder instead of using the decoder element. So in this new version, we've cleaned that up, and now we're using a 3 to 8 decoder, which is much simpler, looks a whole lot cleaner, but is doing the same functionality. These lines are going to the same bits, the same switches as before. It just looks cleaner. And then you can see down here, instead of having that muckety-muck mess with all of the switching to enable whether we were adding or subtracting. We just have two adders. One is being negated to subtract, and the other one is just adding. So just a much cleaner circuitry. Kept things smaller, but essentially the same. So there we go. That is Arithmetic Engine changed. And let's see. Before we get into registers and then the calculations and the program and everything, we're going to talk about conditions. So our default conditional circuit basically had all of these inputs, or sorry, outputs of this byte splitter being merged together into this NOR gate. Well, circular dependency killed that, so all I did there was just ORed the outputs. And I could have used a 3-bit ORs, I guess, but I just decided to go with individual ORs. Oh, no, I did use 3 inputs. These two are actually 3-input ORs, and that's just a 2-input OR. Going to an OR gate and knot it out. Still a NOR gate because of this knot. Just, it's a little bit bigger, and actually somehow this looks cleaner for some reason. So the conditionals, if we look down here, you can see that the bit code, which is coming up here, which is going to be the 3 least significant bits of a program code of, like, say, an 8-bit piece of code. The 3 bits on the right, the least significant bits, 1, 2, and 4, are what's going to set this condition. And then this actual second byte splitter is going to be the value of whatever we're trying to figure the condition out on. And so if our opcode has no 1, 2, and 4 bits, then the condition circuit's never going to work. If the value is equal to 0, that's what we're looking for. So if the value here is equal to 0 and bit 1 is turned on from our opcode, then that's going to come down in here, and then we're essentially going to enable this side of the AND gate. This AND gate is already enabled because there's no value here. That's going to output this AND gate, output this OR gate. It's exclusively one side of this exclusive OR gate, output out, right? So that's kind of how this is working. It's just basically looking for, do we have less than, greater than, equal to, not equal to, 0, always on, never on, that sort of deal. That's what the conditioner is looking for. So once again, the big change here is just we had the circular dependency issue. The instruction decoder worked just fine. I believe the component factory has the same thing as before. So registers, we're going to step through all of these, even though the circuit that you're about to see is the final product, because as we learned in the Arithmetic Logic Engine section, the game said we are now going to build off of everything you're currently building is going to just keep stacking on. So everything is going to just maintain whatever you've done. So registers is going to have everything all the way through on it, but we're going to explain what is different here and what is specifically just for this level. So this is actually our Turing Complete working computer. However, this I even renamed this level. Update ruined me. Essentially, for some reason, my original circuit, because we've done registers and the calculations before, but my circuit was all jacked up. I tried to fix it, and it just kept messing up. So I had to go back to the drawing board, and this is kind of what led me to having the break that I had of not doing this video, was because I was just frustrated with the game and some of the updates they did. But so let's get on. So blah, blah, blah. Forget about all this. Blah, blah, blah. Okay, in this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determines the source and the destination. Bits 1, 2, and 3 give the destination. Bits 4, 5, and 6 give the source. Continue. Source and destination can be one of 6 registers. We'll be named them registers 0 through 5, respectively. Additionally, this map has a dedicated input and output component, which can be source, and output component, which can be destination. And then, so here's just talking about your source and your destination and how the registers will be assigned. And so what we have here is, if we're going to look at it, here's our input, here's our output. Our dark blue line here, which is going all the way across, is our bus. So we've got our bus coming up into these registers that are placed for us. We can't move these now. So all we are worried about in this level is going to be the dark blue line going into the save value function of the register, the dark blue line coming out of the load output portion of the register pin, and then they're all connected together. So boom, comes all the way down to the output. So that's all we're worried about. Input to output, blue line going into the register, blue line coming out of the register. That's all we're worried about here. The next thing we have to worry about is, I believe when you first start this level, they give you like an actual input bit to simulate the opcode, which is now removed because of other circuitry that we've added. But essentially, just think this byte splitter right here. The byte input would go straight into this byte splitter, and then all we're doing here is taking all of our, byte, turning it into bits, and then we're going into two 3 to 8-bit decoders. And if we look at our instruction code here, what we're looking at here is, so bit 1, 2, 4, and F, well, actually 1, 2, and 4, right? So 1, 2, and 4, if all those are turned on, I believe, does it give us, oh, okay, so we can actually create an instruction there. We'll have to actually go through the documentation here. Come on, there we go. So if we're looking at this right here, if nothing is turned on like it is now, then this top line is going to turn on, which goes down to the, well, actually, ignore this OR gate. It should just go directly to the save functionality on the register. If we've got a 1-bit input down here, boom. Actually, why are both of those 2 and 4 turned on? Why are 2 and 4 turned on? What is going on here? Stop. What the hell is going on here? Oh, it's because our program is loading. We can't do this individually, unfortunately, because our program is actually assigned to this. That is hilarious. So basically, you can see here, say, or in this case, 2 and 4 bits are turned on because of our program code. Then 2 and 4 coming down into here. If we look at our little schematic here, then that is going to be, actually, it's flip-flopped around, right? So we have to look at this from bottom to top to simulate left to right here. So now we're going to input. So if we come down here, these lines, you see this gray line is turned on. This gray line is coming all the way down. Do I have these backwards? Why am I not scrolling very well? There we go. Okay, so yeah, so this line, the top one goes to the save function and the output enable. The second one down here, this decoder is going to the load function, and then the bit 6 is going to the enable of the input. So all we're worried about in the register circuit is byte splitter, good lord, going to 2, 3 to 8 decoders. Those decoders are outputting to the save function, to the output enable, to the load function, to the input enable. Then you've got your bus line going to the input of the register, coming from the output of the register to those. That is it. That is the register circuit. So all the other gobbledygook can be ignored. Yes, it's kind of a hard deal to talk about this with everything else there. But so purple, green lines, yellow, orange lines, these 2 brownish gray lines, these 6 white lines connected to the byte splitter and decoders. You would have an actual input right here. And then your blue, dark blue line. That's it. That's all that matters. So we're going to move on from there. Hopefully that makes sense. Now we are on to calculations. So calculations says, time to merge in the arithmetic engine circuit you made previously with the register circuit. The calculation circuit was saved in the component factory and can now be added as a component. If you forgot which pin does what, check the circuit in the component factory. You can also just click on the component and then it'll display down here at the bottom. Use the decodes you built to figure out if you should copy between registers or do calculations. Here are the 4 different modes again. Immediate is both of the decoder turned off. One, which would be A input turned on is calculate, B input turned on is copy, both turned on is condition. For this level, you only have to worry about the copy and calculate mode. And we can click on this little symbol up here and it'll show us the instructions in the top panel for the details. When in calculate mode, take the outputs of register 1 and 2 as the inputs to the ALU and save, so the output of the ALU to register 3. For this level, an extra pin has been added to the registers. This pin always emits the value of the register regardless if load is selected or not. So all they're saying here is this bottom pin is always output. So we're going to use the always output feature of these registers to go to our ALU. So right off the bat, they've told us register 1 and register 2 are going to go to the inputs of our ALU. So you can see here I've added in my ALU and we've taken the always on output of the register directly to the inputs here. So now we need to enable that we're calculating with the ALU. So you can see here we've got instruction is coming from up here, and it's going right off of our input. So the same code that is turning on our byte splitter to select whether we're saving or loading and enabling an input or output is just going to come straight around, and it's going to go down to this ALU. We also need to enable whether we're going to read onto the bus the output of that ALU. So what we have here is this lime green line is coming off of a switch from the output. So you could still do a calculate function, but not output, right? So we could have the always on felt on this ALU, and the ALU does a calculation, but if we're not in calculate mode, this switch won't enable to allow an output onto the bus, and that is just coming from this decoder, which we built in a prior episode. And you can see the opcode is just coming from this byte splitter down and directly into this decoder. So it would essentially be, our new circuit would be this white line coming off this byte splitter into the opcode of the decoder, and that's where it would cease to be, and then it comes up and around to this ALU opcode input. That's it. This white line does not exist for your current functionality. These white lines down here do not exist for your current functionality for the calculation level. So the brown line here also does not exist because we haven't talked about immediates. The yellow line here coming off the decoder does not exist because we're not talking about conditions. All we care about is copy and calculate functionality. So we've got, it's kind of a little bit backwards here, but so copy, well, no, it's not backwards. It's just the way I'm using it is that if copy is turned on, it disables our ALU. If calculate is turned on, it disables our copy functionality. So that's all these two lines are doing here. Our opcode is enabling copy calculate, which then goes to a disable pin on our 3-bit decoder to disable the decoder if we want to calculate. Vice versa, if we want to copy, we would disable the output of our ALU to allow to copy. So this blue box right here with our decoder, these white and lime green lines coming up off of the decoder to our disable inputs of this decoder and to the switch on the ALU are the new bits added. The ALU is added along with the white line for the opcode on both the ALU and the decoder. And then we have an output line coming out of the ALU just back into the output bus line. And then we've got register, not output line. It's basically coming in to register 3, and then we've got the output always on for register 1 and register 2 going as our inputs to our ALU. And because it wants us to save into register 3, right, the last line that we have coming off of this calculate line comes all the way down to an OR gate on register 3's save function. We didn't use a switch because we want to also still be able to use register 3 during a copy feature. So the green line here is going to be the value for copy, enabling save line for copy. The lime green line is the enable line for calculate. So that's it. So that's all the changes made to calculations. And now let's step on up to program. So this is the first new level that we've never completed before. It's where we left off in episode 6. The instruction input component has been removed. It has been replaced by a program component. Every tick uses the counter to load the next instruction from the program's memory. You must use the counter component you unlocked earlier for this level. So essentially, this big red box gets added in this level. This big red box is going to now take over for what used to be the random instruction that the game gave to you. Now it's still a semi-random function, but essentially the way this red box is going to work is from left to right, top to bottom. Every tick of the game, we're going to move from 182 to 134 to 176 to 129, 142, 130, 150, so on and so forth. And then we're outputting from this program counter directly to the opcode of our decoder, which is doing our calculate and copy functions. It's going to go up to the byte splitter all the way around to our ALU. So that's our code instructions for the ALU, our code instructions for the copy function, our code instructions for whether we're going to copy or calculate at all. And the way that this is going to step through this program is using the counter. Now, you're going to have some sort of clock functionality with a counter. So what the game does is it's just going to act as a counter, and every tick it's just going to increment this counter up by 1. So it'd basically be like this pin right here with this white line that doesn't exist when you do program, but this line right here would be like the game's way to say, increment this up to 1, to 2, to 3, to 4, to 5. So you'll actually see this number right here change, and that is just then inputting a counter value to step our program through. But otherwise, everything else runs exactly the same. Nothing new is added but just this program and counter. So if we step it through, you can see copy input to output. So our code right now is 182. 182 is being felt on our decoder here. The decoder, if we look up at our component factory, and let's go to decoder, our decoder only cares about 128 and 64, so bit 8 and 7. So if we come back to our little circuit here, we're going to have to tick it again to get our 182. So 182 means that we're going to suffice to make 128. If we look back at our component factory, you can see that 128, if 128 turns on, boom, right there, you can see we turn on the copy function. Now, if we turn on 64, you can see it turns on the calculate function. So that's all we need to worry about here. Do we have a 128 out of that 182? That's going to turn on one or the other, right? So 182 is turned on, and that's going to turn on our calculate function, or sorry, our copy function, which then comes up through here. Make sure that the disable for the decoders is not turned on, so that way we are actually enabled on our decoders. However, we are not turned on our switch here, so our ALU is not going to work, so we are in copy. And so now if you come up here to your byte splitter, right, so we've set the instructions for the copy function. We've also put this value on the ALU, doesn't really matter. But our byte splitter here now only cares about anything bits 0 through 63. That's all the byte splitter cares about. So 182 minus 128, you're going to get 32, 16, 4, and 2. So we've got 16 and 32 coming down. That suffices to make bit 6 on this decoder. Bit 6 on the decoder enables the input to be turned on. And similarly, you've got 2 and 4, which makes bit 6 on this decoder, which is going to turn on your output. So the problem here is copy the input to the output. Here's the input. It's enabled, goes right along the bus. The output is enabled. Boom, you've got the input on the output. Let's do one more tick. So we're going to copy register 0, which is this register right here, and we're going to copy it to the output. So our opcode here is 134. So 134 minus 128 means we're going to get a copy function. The leftover of 128 from 134 is a 4 and a 2. So right now you've got nothing felt on this decoder, which means register 0 is selected for the load functionality. Down here, you have the input enabled for the actual input. So it's going to come all the way down here, and you're going to get the value of 0, which is what they've set here. And the value, I got to step it through, right? Well, it doesn't really matter. Same thing. Now it's just a value of 168 to 0. So, or why is it 197? They want 168 from the input. That's 197. Are we supposed to be like this? Nope. I don't know. I have no idea why. Copy input 168 to register 0. This isn't 168. I don't know what the hell's going on there. They've got the wrong input value. But you can see that if the input value is 197, it's being copied to register 0. Register 0 to register 1. So now we're going to essentially, oh god, oh, I got the hiccups. 129, so our decoder, 128 is met, so we're in the copy function still. Cool. There's only a 1 value left over. So register 0 is saved for the, register 0 is loaded. Register 1 is now in the save function. So we're loading the value of register 0 out to the bus. The bus comes all the way down, all the way back up, all the way around, back into register 1 to be saved. So on and so forth. And why did that not work? Copy register 1 to output. Oh, because we've been toggling and clicking things. That's why this is all jacked up. Yeah, see, there you go. Now if we step it through, it's working. I had clicked on some stuff. But yeah, so there we go. So that is all that was done to the program. You literally just add the red box, and a counter is the input to the red box. That's it. So this right here, just this counter, this white line, this program, this white line. That's all that's added. Hope that makes sense. Now on to the second to last, immediate value. So we'll read the description here. We need a way to directly move numbers from our program into registers. For this, we use the immediate mode when both the two highest bits are set to off. So the 128 and 164 bit from our program are turned off. We're going to use the immediate function. When in immediate mode, the whole byte is interpreted as a number that we save into register 0. This means we can save any values between 0 and 63 because essentially we're only using 128 and 64 for the decoder. The rest of the value is going up. So all we have here is now on our decoder, we have the immediate function, right? So it says we want to save the immediate function into register 0. So we're going to come up here with our line off of our immediate. We're going to take this down to an OR gate to our save functionality, just like we did before with register 3. And we're going to OR this with the save function of register 0. So that way we can either copy with a save or we can immediate with a save to register 0, because that's what the problem specifies. Also, we need to take this value that is the opcode coming over here, and we need to be able to place that on the bus. So I've just extended the bus line up, added a switch, and we've got an enable line coming from that immediate register to enable the switch, and then the input of the opcode is going directly onto the bus. So that's all that's added into the circuitry now, is this brownish gray line is going to come down to an enable to save to 0 and an enable for the actual opcode to go directly onto the bus. That's it. That is all that is added with this circuitry here. And if we tick through, you can see immediate 63 to register 0. So our program is actually labeled as number 63. So 63 is felt up here. 63 is less than the 128 and 64, right? So we don't have anything but the immediate value felt. So immediate is turned on. Immediate comes over and is OR'd into the save function of register 0. Also turns on this switch for the opcode, which where we have coming all the way up, comes all the way around on this white line, felt on this new piece of blue bus that we added, and boom, it comes down onto the bus, back around, and then inputs into register 0. Let's do one more. So now if we changed over to copy input 0 to register 1, now we've turned off the immediate value because our program line is 177. So we get our 128, which is the copy functionality. The leftover remainder is 49. That 49 is, oh God, that 49 is felt up here, saving to register 1 and also enabling the input. And so you're going to feel that input out. Which is basically they just wanted this to go up to here. So yeah, so there we go. So like I said, that's all that changed, was adding in this gray line for a switch to add the opcode to the bus, this OR line, so we can either copy or immediate to register 0, and then added actually the output of the decoder for the immediate line. That's all that changed there for the immediate values. Now on to our final spot today, the Turing Complete Working Computer, which is all of this. So it says, until this point, all possible programs have been confined by running in order byte by byte. So they're telling us to byte by byte, you know, step 1, step 2, step 3, step 4. Before, only code could influence memory. Now memory must influence code. With the addition of conditional logic, our computer can run any algorithm and calculate anything calculable. The final thing we need is to add is a mechanism for changing the program counter through instructions when certain conditions are met. When the two largest bits, so our 128 and 64 on our opcode, are on, we are in a condition mode. In condition mode, the value in register 3 is compared against the conditions defined by the lowest 3 bits, 1, 2, and 4, in the instruction. If the condition is true, we overwrite the counter to the value in register 0. Conditionally changing the counter means we can skip instructions based on conditions or have instructions run in a loop. So once again, we've looked at this before. If any of these, so this would be bit 1, bit 2, bit 4 are made in this. So if register 0 equals 0, then we have to have a condition of bit 1 from our opcode. Condition of register 3 is less than 0, bit 2 has to be on in our opcode, so on and so forth. So these conditions correspond to the condition component that was saved in the component factory. So all we've done here they said that we need to look at register 3. So this is register 3. So we're going to take the output of always output, and we're going to come back around. That's this lime green line, and it's going into our conditional circuit that we made earlier. That is up here in our diagrams, conditional 4, boom, right there. So this right here, this bottom portion with all these OR gates is the value of register 3's output. That's what's coming in to this conditional circuit. These 3 lines up here coming off of this top byte splitter is the bit 1, 2, 3, or 1, 2, 4, the least significant bits from our program code. And that's what's going to do all the conditioning and look for an output here. So we've got our output coming from register 3. That's coming over to our conditional. We need to add in the input for our conditional, which is coming from our program code. So all we've done here is grabbed a line from our program code to input in. And then we need to have an enable circuitry for this conditional, because we don't want to just always have this being done, because if a condition is meant to be true, but we're not trying to jump the program, then we don't want the conditional output to work, right? So if the program is set as such to make the condition for both the 128 and 64, the 2 most significant bits of our code being turned on, then this conditional line will go to an AND gate and turn on if there's a true statement coming out of our conditional, and then that's going to come down to the increment / overwrite value of our counter. And then also up here, what you have is coming off of register 0, because what did they say here? Boom, boom, boom. Yeah, so if the condition is true, we overwrite the counter to the value in register 0. So whatever value is outputting from register 0, if this conditional is made, we're being told to do a conditional, and the conditional is true, then that's going to increment the counter to whatever value is felt here on register 0. And that's what this lime green line coming up over the top is, coming down into, or not lime green, green, coming into this conditional. And what that's going to do is whatever value is stored here is wherever we're going to jump into the program. So the program is 1, 2, 3, 4, 5, 6, 7, so on and so forth. So if our conditional is met and say the register value is 63, it's going to jump all the way down to line 63 in the program code. So that's all that has changed here. All that's been added. This yellow line coming over to an AND gate, this conditional, which is coming from the opcode for the input, and coming from the output, always on output of register 3, ANDing it together, going to the increment bit of the counter. With the value of register 0 is the value to overwrite bit on the counter. That's it. That's all that got added to make a Turing Complete computer. So now if we step it through, you can see copy input, value of 1 to register 1, which is being done. And that is being done because we have 177, which makes the 128 to set the copy functionality. 32 and 16 comes down here to load input. The value of 1 comes down here to save to register 1. The input of 1 is enabled, getting put on the bus, going through the functionality of the save of 1 and being stored there. And then, of course, it is being output to the bus, but it's not going anywhere because, the output of the bus is actually felt right here as well. So it's not being outputted because it's not being told to load. It's just being felt on this side of the bus. So the next step is input 2. So we've got a value of 2 to register 2. So once again, we've got a output code of 178, suffices to make our 128, which is the copy functionality. 32 and 16 come down here to load it, to enable the input. Our bit 2 comes up here to come down to register number 2. Same thing. You've got input enabled, comes onto the bus to the save enabled, register 2. You get a value of 2 stored in there. Now we're going to subtract. So I believe... yeah, I kind of need to do this. I need to put us into to sign negator here so we actually get our subtracted value. But subtract, right? So our program is 69. So 69 minus 64, that works. So our calculate function is turned on. So you can see the output of our ALU is enabled along with this down here, which is where we're storing our ALU value. So we're enabling the save function of register 3. And then we come up here and we've got no value on our second decoder, so we're not loading anything. We've got, which wouldn't matter anyway because we're disabling both of these decoders. So ignore that altogether. Our decoders are disabled, so we're not copying, we're only calculating. So with calculation, all we do is take input of register 1, output of register 1, output of register 2, going to the inputs of our ALU, which I just moved because I'm a dum-dum. Boink, there we go. And so 2 minus 1, or 1 minus, 1 minus 2 is a negative 1, and we can see that right there. And because I moved that bit, of course, did it stop this and go back through? There we go. So 1 minus 2 is a negative 1. Boom, there you go. You see that negative 1 coming around. It actually comes down this way, comes back up the right side of the bus, and gets stored into register 3. Good Lord, that was a mess. All right, step up to the next one. So now we got our first conditional. If register 3 equals 0, counter equals 0. So register 3 equals 0. It sure as hell does not. It's negative 1. So we got the value of register 3 coming up here. And we've got our conditional met because we are negative 63 is the program code, which sure as hell doesn't equal 64 or 128. Let's go back to 255. There we go. So now, okay, there we go. That's better. Now we're 193. So we meet both 128 and 64, which satisfies the requirement for both the two highest bits to make the conditional circuitry, which comes over here to enable this AND bit. And then we've got an input of our opcode is 193. And so that is going to, let's come over here. 193 is being felt on here. Let's go back. I am an idiot and I can't remember things. What is that going to be? Boom, boom, boom. Boom. Here we go. 193 is going to be just a number 1 left over. That's what I couldn't remember. So number 1 left over. So this is what's coming from our opcode. The 1 left over. And then down here we had, what was the value? What was the value? I don't remember. There we go. The value is 255 coming up here. So we've got a value of 1 from our opcode and 255 coming from our register 3. Because without sign negator turned on, it can't do the proper subtraction, so it'll just give you 255. So there we go. So everything is turned on for coming in through the actual value of register 3, which means everything is turned on with these OR gates. Inverted means it turns off, which means this 1 bit from our opcode going to this AND gate does not suffice. This AND gate's not made. And since we have no bit 2 from our opcode, it doesn't matter that our 128 bit from our register 3 is made. This AND gate does not suffice. No input to our OR gate. No output from our OR gate. The exclusive OR does not have anything exclusively on. No output from our component factory for our conditional, which means we got to step this back through. I hate how it does that. If I go to my component factory, this should remain on the tick that I'm on. So this does not make a true statement, which means this AND gate doesn't get made. So there's no output from our AND gate. So we are still on step 4 of the counter. We do not load register 0's output onto the counter. So let's step it through again. Immediate 7 to register 0. So register 0 is going to be right here, and we are going to take the program code, which is 7. We are not meeting anything, which means we're going to use our immediate line. So our immediate line gets made, comes over here, ORs it to get the save function of register 0. We're also taking what's on the bus, and I believe how are we doing this? Yeah. So we're enabling this switch, which is taking the opcode directly onto the bus. Bus comes around, comes back up to register 0, which is enabled to the save. So we're immediately saving that 7 value into register 0. So as you can see, we can condition, we can add, subtract, we can copy, we can immediate, and we can jump around the program. We can do everything with this computer now, all on its own. And so I will kind of do a little sweep here through the program, well, not program, through the level, so you can kind of get an idea. You can pause the screen as needed. So this is our conditional circuitry coming off of our decoder, which has as conditional on the right, copy, calculate, immediate. You've got your AND circuit to enable this conditional if it's made true and being selected to actually run a conditional. You've got your counter for the program, which is right here. Program outputs the opcode, which goes to the input of the decoder, input of the conditional, input of the byte splitter to select the save and copy functionality. The save decoder also has the output enable line. The load decoder has the input enable line. You've got the calculation function enables an output switch from your ALU. Also, because of the way the program wanted you to do it, they wanted you to store the value in register 3. So we have an OR gate, ORed between copy and calculate functions to actually save to register 3. Your calculate line comes up here to enable or disable your decoders, depending on, it'd be disabled if you're calculating, it'd be enabled if you're copying. And then coming down with the functionality there. Then you've got your conditional, which we already talked about. You've got your bus line here, which is the dark blue, being connected to both the opcode and the input and output down here. And then your ALU is the input, is coming from register 1 and 2's output. And there we go. That is a Turing Complete computer. So hopefully that made a little bit of sense. Hopefully you guys understood it. But yes, we made progress finally. I know it's been 6 months and I apologize, but woohoo, we are Turing Complete. Next thing is to get on to programming, and oh god, I hope this is machine code programming and not actual, like, you know, Java, C++ or whatever, because that is, I am terrible at it, so it's going to be a fun learning experience together. But anyway, guys, I'm so sorry for it taking 6 months. I hope you guys enjoyed this. I hope you learned something. If you have anything to share that shows an improved version, a different version, a unique way to do the solutions for these, or just want to discuss some generalities on how real-world computers work versus the in-game computer or a Minecraft computer or whatever, definitely comment down below. I'd love to hear your thoughts on it, and hopefully the next episode will be out much sooner than 6 months. But my brain hurts now. That was a lot of talking. There was a lot of explanation. I hope everything made sense. But until next time, ta-ta for now. Bye. With